The term dwarf star refers to any star of average or low luminosity, mass, and size. There are important subclasses of dwarf stars, such as white dwarfs and red dwarfs. Main sequence stars, such as our Sun, are also classified as dwarf stars, whose colors take several ranges from red to blue according to their photosphere temperatures that can be more than 10,000 Kelvin or reach a minimum of a few thousand Kelvin. Curious to learn more about dwarf stars and their types? Keep watching. As we mentioned earlier, main sequence stars are classified as dwarf stars. It's logical to say that most of the stars in the observable universe are dwarf stars, since they are in the main sequence of their life cycle. The main sequence phase is the longest phase in the lifetime of any star. The characteristic feature of this phase is the thermonuclear fusion of hydrogen into helium in the star's core. The star usually gets cooler, brighter, and bigger once it runs out of the hydrogen fuel in its core. Therefore, any typical star gets bigger before dying. Although the main sequence stars are referred to as dwarf stars, they are quite large. Even some of them are several times larger than our Sun. Our Sun is classified as a G2V star, where G2 refers to a photosphere temperature of 5,500 Celsius, and V refers to its dwarf status. There are some special dwarf classifications that designate small classes of stars. For example, red dwarfs, brown dwarfs, yellow dwarfs, and white dwarfs. 1. Red dwarfs, which are the smallest and coolest stars in the main sequence. Additionally, they are the most common type of dwarf stars in the Milky Way. In fact, they constitute 3/4 of the Milky Way. However, they cannot be easily observed due to their extremely low luminosity. The closest red dwarf to Earth is Proxima Centauri, located in the southern constellation of Centaurus. Red dwarfs are very low-mass stars, with masses about 7.5% of the solar mass and 9% solar radii. These conditions result in low gravitational pressure, which in turn leads to low thermonuclear fusion rates that eventually lead to low temperatures. The proton chain mechanism is the way by which hydrogen is fused to helium, which releases tremendous amounts of energy, mainly via convection. However, helium does not accumulate in the core of low-mass red dwarfs since they are very convective, which makes them burn large proportions of hydrogen before leaving the main sequence phase. The low nuclear fusion rates in the core, along with the convective feature of the low-mass red dwarfs, result in their extremely long lifespans, which are approximated to be longer than the age of the entire universe. 2. Brown dwarfs, whose masses are less than 0.08 solar masses. The internal temperature and pressure of the protostar is insufficient to induce thermonuclear fusion that is necessary to fuse hydrogen into helium, which makes the protostar a failed star, and it's called a brown dwarf, midway between Jupiter and any regular star. To illustrate this, stars radiate light and energy due to the fusion of hydrogen into helium in their core. However, the temperature of the core must be at least 3 million Kelvin for the nuclear fusion to occur. And due to the fact that the core temperature increases with increasing gravitational pressure, the mass of the protostar must be at least 75 Jovian masses, or 0.08 solar masses. The dwarf star barely marks that limit. It's more massive than any observed supergiant gas planets and not massive enough to be a star. Despite the fact that they are named brown dwarfs, their colors vary and take a wide range, such as orange, red, or even mostly magenta. The existence of brown dwarfs was theorized by Shiv S. Kumar in the 1960s. In his theory, Kumar named them black dwarfs and defined them as dark substellar objects floating freely in space that were not massive enough to sustain hydrogen fusion. 3. Yellow dwarfs, which are stars of medium size, such as our Sun. A typical yellow star belongs to the main sequence and has a spectral type G, weighing between 0.84 and 1.15 solar masses. Yellow dwarfs make up 10% of the total stars in the Milky Way. The surface temperatures of yellow dwarfs reach 6,000 degrees Celsius, which makes them shine bright yellow, almost white. Yellow dwarfs become red giants and white dwarfs at the end of their lives. A typical G-type main sequence star is burning hydrogen into helium in its core by means of thermonuclear fusion. Our Sun, for example, converts approximately 600 tons of hydrogen to helium per second via the proton-proton chain mechanism, in which 4 hydrogen atoms form 1 helium atom. Alpha Centauri A, Tau Ceti, and 51 Pegasi are well-known examples of yellow dwarfs besides our Sun. The ultimate fate of yellow dwarf stars is that they will turn into small, dense white dwarfs after evolving to many phases. First, once the yellow dwarf runs out of hydrogen after approximately 10 billion years, it expands to larger sizes of its original volume and becomes a red giant. However, at a certain point, the inner core reaches a typical density at which the degeneracy pressure cannot support the core against its own gravity, sending shock waves to the gaseous outer layers, which eventually are shedded to form planetary nebula. The core then cools and becomes a white dwarf, whose chemical composition is carbon and oxygen. Aldebaran, or Alpha Tauri, is a good example of red giants, with luminosity 518 times the solar luminosity and located around 65 light-years away from the Sun. Before moving on, be sure to like or dislike the video so that we can continue to improve our content and make these videos better for you. Plus, be sure to subscribe to the channel and don't forget to hit the bell button so that you don't miss any of our weekly videos. 4. White dwarfs, also called degenerate stars, which are composed of electron-degenerate matter. White dwarfs are very distinct astronomical objects. Being stellar remnants, they are extremely dense. A typical white dwarf has the mass equal to the Sun trapped in a small planetary volume that is comparable to the volume of the Earth. There's no thermonuclear fusion that takes place inside the white dwarf. However, its faint luminosity is due to the stored thermal energy inside it. White dwarfs puzzled many scientists throughout the last century. In particular, Eddington, who argued in 1924 that white dwarfs have extremely high density and hence very strong gravitational fields that cause the light emitted from them to be redshifted, according to the theory of general relativity. Eddington's estimate of the gravitational redshift of Sirius B was then confirmed 1 year later by Walter S. Adams at the Mount Wilson Observatory. In 1928, Pokrowski, a Russian physicist, published a paper about the limiting density beyond which a star collapses. In his paper, Pokrowski claimed that a star will collapse if its degenerate electron pressure can no longer support its core against the gravitational pull. Nearly a year after that, Wilhelm Anderson modified Pokrowski's idea. He repeated Pokrowski's calculations and came up with an idea that a star reaches its limiting density because of radiation. Provided that E equals mc squared, there is an equivalence between radiation and/or luminosity and the star's mass. That is, when a star radiates energy into space, it contracts and decreases its mass. The idea of a star's limiting mass was then demonstrated by Edmund Clifton Stoner in his papers. He argued that the limiting density might exist due to the squeezing of electrons, which obey Fermi-Dirac statistics in a small volume, not due to the full ionization of matter, as Pokrowski claimed. Moreover, he was highly dependent on Jeans's theory of stellar stability, which states that a star that satisfies the ideal gas laws cannot be stable. Anderson then made an analysis of the electron gas in white dwarfs to check if it satisfies ideal gas laws or not. Also, he claimed that as the density of white dwarfs increases, the electrons are driven to higher energies and quickly become relativistic. Stoner then came to the picture with a modification to Anderson's mathematical treatment to the problem, and he finally accepted the role of special relativity in approaching it. He demonstrated that the density approaches infinity as the mass reaches the limiting mass. In 1930, at the age of 20, Subrahman Chandrasekhar, the Indian astrophysicist, calculated the correct mass limit above which the white dwarf cannot exist. He took into consideration the effects of special relativity and applied a better model for density distribution in white dwarfs. It is so important to indicate that Clifton Stoner derived a mass limit, and it was about 2.5 solar masses. However, to simplify the calculations, he assumed that the density in the star was uniform and did not change from the high density in the center to the vanishing density on the surface. Eventually, the underlying assumption of uniform density caused him to lose the priority in the discovery of the white dwarf's mass limits. To sum this up, white dwarfs are distinct objects with stellar masses and planetary dimensions. Their stability is governed by gravity and quantum mechanics, and according to the Chandrasekhar mass limit, there is a certain mass above which white dwarfs cannot exist, and it equals approximately 1.4 solar masses. They are also massive hot conducting spheres sheathed in a thin but very effective blanket of insulation, according to some studies regarding their thermal structure. Moreover, the chemical composition of white dwarfs depend on the initial mass of the star. If the initial mass is between 0.08 and 0.4 solar masses, then the star will be a very low-mass star that's too cool to fuse helium into carbon and oxygen. It will end up as a white dwarf made of helium. However, if the initial mass is between 0.4 and 4 solar masses, then the star will be a fairly low star that's too cool to fuse carbon and oxygen into heavier elements. It will end up as a white dwarf made of carbon and oxygen. In conclusion, stars are very dynamical objects whose behaviors are governed by many macroscopic and microscopic features. They exist in numerous shapes, sizes, and states, and these varieties determine the fate of any star, since we all know the fact that all stars evolve through the course of their lives. Stars spend most of their lifespan in a phase called the main sequence, which is highlighted on the Hertzsprung-Russell diagram, or HR diagram. The most important feature that highlights the main sequence stars is the thermonuclear fusion of hydrogen into helium in their cores by the proton-proton chain mechanism. The main sequence stars are also considered to be dwarf stars, despite the fact that they are quite large. In fact, several times larger than our Sun. The dwarf stars are classified into many different types, such as red dwarfs, brown dwarfs, yellow dwarfs, and white dwarfs. Red dwarfs are only a fraction the size and mass of the Sun, and can be as little as 1/10,000th the Sun's brightness. Because they are so cool, their surfaces are orange or red. Brown dwarfs are failed stars, since they have extremely low masses that are insufficient to induce thermonuclear fusion inside their cores. Yellow dwarfs are medium-sized stars like our Sun, which in turn is classified as a G2V star. White dwarfs are the dead cores of once normal stars. They typically are less massive than the Sun and only about the size of Earth. They are extremely hot and dense, although they no longer produce nuclear reactions. Thanks for watching, everyone. Have you understood how dwarf stars are categorized? Do you know what governs the stability of white dwarfs? Or what's their energy source? Let me know in the comments below. Be sure to subscribe, and I'll see you next time on the channel.